With that, I'll move on to Nick Miller. Nick Miller is an internationally known power system engineer with the specialty in integration of wind and solar generation to the bulk power system. He spent 3/8 of a century with GE. He is an IEEE Life Fellow, a licensed professional engineer in New York, and a distinguished member of Seagray. And Nick, I'll let you tell us a little bit about the U.S. hydropower system.
All right, thanks, Josh. Great to be here. And I need to add another fraction. I realized on Saturday I will have been retired from GE for 1/20th of a century. So a lot of these things are no longer arithmetic. That's my friend. Okay, so I could talk a little bit about hydro today. And you might wonder what, right? So I'm not a hydro guy. And in fact, so how many people in this room consider themselves to be hydro people? All right, that's great. All right, but you are very much in a small minority, and it's been a source of some concern to me that I raised with Charlie and others, that the wind and weather dependent variable wind and solar communities don't communicate and coordinate very well with hydro. And a lot of our decarbonization discussion is in this room, right, is about the displacement of fossil resources. So we say, well, we're losing this service, that service, because we're getting rid of the coal, but we're not trying to get rid of the hydro, right? At least not in general. And the question arises: is the renewable community, is the wind and solar community really working very well with the hydro community? And it is my perception, and I'm learning that perception has got at least some elements of truth, that the communities are too isolated from each other. So there's some, a little bit of the work I'm going to talk about today is a consequence of me sort of stirring the pot, and was funded. So Simonelli, our absent, but here in spirit, colleague, and I did some work, and we're getting too long in the tooth to actually do any number crunching, so we sit around and pontificate, which is what this report is. But the question here really is, okay, we are probably in North America not going to build a lot more hydro, but we don't really want it to go away. So now we're going to have hydro resources that are working in a world that looks quite a bit different. And yeah, those kilowatt hours that come from the hydro are zero carbon and they're nice, but what can we do differently to make the hydro be an asset that hits above its weight, so that every kilowatt hour of hydro or every kilowatt of nameplate of hydro enables decarbonization more vigorously than simply the one-for-one change out of kilowatt hours. So that's kind of the backdrop on this. And I'm going to go through 3 little bits of this story in my 20 minutes or less. I want to make sure I leave time for the rock star because the Kauai system is so wicked cool. Anyway, never mind. So this work started in New England. I'm just going to put a couple little cucaracha examples up that are sort of teaching your grandmother to suck eggs, frankly, for this audience. And then I'm going to talk a little bit about some heresy, and then I'm going to go completely afield and talk about people out there that we don't in this room talk about at all, and we should be. So, I'm getting long enough in the tooth that the only tool I know how to use is a spreadsheet anymore. So this is an Excel exercise from when John and I were doing the work of a day that was of note to ISO New England for having the lowest minimum net load that they'd recorded to date. And it happened in the middle of the day, and that's that orange curve up there. I know you're trying to make these things relatively simple, and everybody got very excited. That's 8 gigawatts of net load in a system that peaks at something like 28.5 gigawatts. So whatever that ratio is, that got people pretty excited in New England. There's a lot of generation that wants to stay online all the time and starts to back down. And you see the solar curve, and we got an evening price spike, and that's all stuff that everybody in this room sees all the time. So I went forward and we did that work in 2020. 2022, I picked exactly the same day, which happened to be a nice sunny day. And the curves up there up top, you don't need to torture yourself, but basically not much change other than the evening peak was a little bit spikier, but the price of electricity is now that upper curve, which barely is visible. So we got the joy of these projectors there a little bit. Price of electricity in May 2nd, 2022 was 3 times what it was on May 1st, 2020. All right, didn't see that coming. So a lot of the hydro community sits here and sees these projections of the value of their assets, the value of pump storage, and yet these forward-looking tools that we have sort of somehow miss it. And I keep coming back to talk about the hydro folks, right? If we had the equivalent room right here, the hydro people, you would find a significant fraction of them saying, damn it, we're the good guys. And you wind and solar people are just beating our assets up. We're having to cycle and it's turning our equipment and we do all this great stuff for the grid and we aren't getting paid for it. And we kind of hate you people. Right? That's not the message right? That's not the decarbonization kumbaya message that we would really like. So the question is, how do you get everybody on the same page? And part of that is getting paid for the electricity, getting paid for the energy. Everybody in this room knows that. So this is looking forward down the path of adding 11.4 gigawatts of offshore wind, which is what's in the queue in New England, and picked a day out of the NREL data set that was also May 2nd. And that 1.4 gigawatts of offshore wind and another couple gigawatts of onshore wind and a couple more gigawatts of utility scale solar and a couple more gigawatts of behind the meter solar. And all of a sudden the net load looks like minus 11 in a system that has generation that can't be shut off and has limited ties to the rest of the world. So we come back and say, what is 2 gigawatts of hydro going to do to help that problem? And the answer is not much, at least not on that scale, other than we can do pumped hydro. So I'm going to give DOE some credit. We started poking on this. DOE has a very nice national data set. It's all published. This is the potential for closed loop pumped hydro all across the country. There's 350 gigawatts of identified sites by their criteria, which are pretty complicated, but credible to my mind, totaling 35 terawatt hours. But in New England, those red dots down there, you have to know your geography to recognize that. There's actually only 9.5 gigawatts of sites, which out of the 350 is actually pretty small. They did a bunch of these forward-looking work at right? You heard this wonderful stuff from Adria this morning, right? Hundreds and hundreds of studies. So one of the data points on her map includes 6 to 7 gigawatts of pumped hydro makes sense in New England. So that's about half of that. Oh my God, what are we going to do from my previous chart? Yeah, maybe that works. All right, so everybody knows this stuff. Let's go on and look for some other benefits that will maybe allow the hydro to be on its way and maybe find a way to get some more revenue so that they can fix their 100-year-old assets that are being cycled and turned into scrap metal, depending on who you talk to, right? So you talk to one person in the hydro community, they'll say that the cycling associated with following all this wind and solar is turning their equipment into trash. And then the next person you talk to in the same industry says, duck soup. I don't know enough to answer that, but it's very interesting to hear this huge spectrum. Okay, so ancillary services, right? This is saying things that everybody in this room already knows, right? Hydro is really good at providing a lot of these ancillary services, many of which aren't paid for. So the question is as the other resources that we depended on go away, and these resources that are capitalized and on the system sit there and decay, are there pricing mechanisms? Are there incentives? Are there other things that would allow us to actually invest in those hydro plants to get the best possible ancillary services, essential reliability services out of them, instead of building new stuff? And the hydro community a lot of times feels like they're off in the wilderness being ignored. And I think some of that is legitimate, some maybe isn't. But how do you get paid for your 30 megawatt hydro plant having superior voltage regulation out in the wilderness of northern Maine, where we would actually like to put a bunch of wind turbines, and having some good stiffening of the grid nearby is very valuable. Oh, sorry, that's not on the planning, right? This hydro plant was built in 1930. Nobody's going to spend a penny on it and say, wait a minute. Okay. So I'm going to go on now to the technologies, some of the cool pieces of technology. You know, this long list, a couple of these orange ones I'm going to talk about. So on the pumped hydro in particular, right? Today's pumped hydro is not your grandmother's pumped hydro, right? You wouldn't build one of these 1 to 2 gigawatt class pumped hydro plants without having it be advanced technology, which is to say variable speed. There's a bunch of variations on the theme. I was coming at this work specifically through the filter of variable speed pumped hydro, which looks, those of you that know my expertise, right? Variable speed pumped hydro, the commercial ones look a lot like type 3 wind turbines. Okay. Some of them look like type 4 wind turbines. And by the way, they are wildly flexible, more efficient over a wider range of operation, and you can jerk them around almost like you can jerk around batteries and make really cool things happen. So this is a thought exercise that we did for NREL DOE funded study. And I know you can't, right? This is a fishhook, right? Those of you that know me know I live this world of frequency control, and I live for these frequency fishhooks, right? And, you know, make things better, go up and down. But the orange is a 2 gigawatt pumped hydro in the middle of WEC, responding at a 200 millihertz frequency excursion caused by trip of 2 Palo Verde units, which many in the room recognize as the design basis event for WEC. And if you shut off 2 gigawatts, which you can do with power electronics, you get a spectacular recovery of frequency. There's really exciting things you can do with this stuff. But, and this is where the differentiation is like, why would you do this? Why do you need pumped hydro? Can't you do this with battery? So this is 2 gigawatts of pumped hydro in one spot. This is some sort of heresy that I'm advocating in this picture, right? This is a RAS. This is some sort of if this, then that control that isn't in the same physical location. Oh my God, right? You are proposing something that we do not do. But it's not really true that we don't do it. In California, they have had a whole range of discrete control actions for years on the big asset known as HVDC. So if you're talking about doing aggressive, interesting controls, if you've only got to do it with 1 or 2 assets, you could color outside the lines. If you ask me to do this with 100 times 20 megawatt batteries, the answer would be the institutional pressure of me making this right is hopeless. So size matters. That's one of the things going for hydro. This is another exercise. My friend Matt's in the room. We did this work for a different client on a similarly sized, the 1500 megawatt advanced pumped hydro in California. And again, the same concept, the idea that you've got this very fine controllability, even when, especially when it's pumping. And in California, this is a production simulation where we've got path 26, right? The cuts across California, north to south at its rating, right? That's standard thing. You throw it in Plexos, the answer comes out. Some hours you're banged up against the limit, right? Those are in the evening of this particular day. But if you look at the ability of this giant pumped hydro to deload that interface, then when it's pumping or under some other conditions, it has the ability to respond to that and buys you extra capability. This particular exercise showed that 93% of the time that path 26 was limiting in this particular year, you got an average of 924 megawatts increased transfer capability, right? So you're against the limit, So there's economic value in moving that limit. This pumped hydro resource is 1,500 megawatts. And it's effectively just bought me 925 megawatts of transmission 93% of the time. You think it might be worth challenging your paradigm that says, no, we don't do that here. Right? Because that's the answer today. We don't do that. Okay. So I can have the equivalent of a 345 kV transmission line for zero capital investment if I'm willing to look at it a little differently. Ooh, heresy. All right, another thing, right? So this is real simple. Back to conventional hydro. I'm back in New England. I've got little, frequently very old hydro plants sprinkled around the countryside, right? Sometimes out on long, skinny feeders, whatever. They provide a really valuable service, a whole bunch of them. Blackstart, for which they get paid essentially nothing. Voltage support, for which they get paid essentially nothing, right? The excitation systems are 65 years old. Why would you invest in the excitation system when you get paid nothing for it? Why would you do something like allow that hydro machine to run as a synchronous condenser all the time, right? You got to evacuate the turbine and let it spin in air, right? It's actually a relatively simple thing to do. Oh, I need a market for that. So I got all excited about that. So these are all over New England. This would be great. And I was given this presentation or a similar presentation to a National Hydro Association group, right? So the other guys. And that happened to be down on a day when they gave us a field tour of Conowingo, which is its beautiful century-old giant hydropower plant on the Susquehanna River. Right? And I was talking about that and they said, oh yeah, this plant's got the ability to do operation as synchronous condenser. We stopped maintaining it. We didn't get paid enough. We don't do it anymore. So Nick's enthusiasm was deflated. I still think that that's a possibility. All right, so there's a bunch of other cool stuff that you can do. The idea that investment in these old capitalized, somehow over the fence hydro isn't worth the trouble is something that we need to challenge. Which brings us to a broader community. 3 minutes, I'll be good. I got involved in this thing called the Stanford Uncommon Dialogue. So in the United States, there's 90,000 dams that are under federal jurisdiction, of which 2,500 make power. All right. A lot of those dams are older than dirt and either need to be fixed before somebody dies or some environmental catastrophe comes along, or they need to be repowered to make better use, or they need to be taken out to restore the ecosystem damage that was done by the presence of it that is not. So there's billions of dollars out there, and there's a massive community that it was completely mystery to me that are asking these questions. Should we do one of the 3 R's, which is rehabilitate, retrofit, or take it out? And you see all these players, sorry, the logos there are too small, but these are not primarily people in the power industry, the folks in this room. There's a lot more to a hydro plant than making kilowatt hours. And we forget that at our peril. This is so I did rapid editing of these slides because they had a lot of small font on them, which proved to be, right? So 1/4 of the members of this uncommon dialogue are hydro people. This is people getting in the same room and thrashing over what should happen to these resources. And it's not done through the filter of let's make some more kilowatt hours. It's run through the filter of our ancestral land has been ruined by this hydro plant. You are causing desperate stress to the fish phrenology. I had to learn that word. Right? By the way this plant is being operated, right? You are adversely affecting the recreation value of this, right? So how do you get all those people in the room? Value is not dollars per kilowatt hour. So these are all the working groups of this thing. The only point here is that the only place where Nick participates, because I think about dollars per kilowatt hour, is box 4. And there's a whole bunch of other stuff going on there, keeping these hydro resources in business, making them meet a societal benefit of which our interests in this room are some little slice, is something that we forget at our peril. So that's really where I wanted to get us to. Valuation means radically different things. And, you know, as power people, we've got to recognize that doing things like following the duck curve, dispatching the hydro aggressively up as the sun comes down, may or may not fit, right, in this bigger picture of value. We forget that at our peril. All right. I got it. All right. Thanks, everybody.
Thanks, Nick. Any really quick clarifying questions for Nick? Great. We'll move on to our final speaker for the late session here. No, it is not a typo in your agenda here. We have Cameron Kruse, not the long lost brother of Andy Kruse earlier today, who will be giving our last presentation. Cameron received his Bachelor of Science in Electrical Engineering from the University of Arizona in 2008. Upon graduation, he started working at the Kauai Island Utility Cooperative as a staff engineer in transmission and distribution. He was promoted to supervise operations on the island's electrical substations in 2011. And in 2020, he was promoted to engineering and technology manager. During his time at the cooperative, he has worked towards transforming the grid's renewable generation from 8% renewable to 70% renewable in 2021. He's a licensed professional engineer in the state of Hawaii. Cameron, please take it away.
Thank you. Can you guys hear me okay? Awesome. I got 15 minutes to get you guys out of here by 5:30. So I went, this is the first time I've been back in Tucson since I graduated. It's nice to be back. And it was funny because the night I graduated, I went up to one of my professors and I was like, how come you guys don't offer any power courses here? And he was like, it's not cool. Power's not cool. And I was like, I beg to differ after coming here and hearing everything, what everyone's doing outside of what's going on in Hawaii. You know, you think about Hawaii, you think about tropical paradise. People are on Hawaii time. Things are a little bit more laid back, slow. Not for the power industry. Things are accelerating beyond what we can even model, and you guys will find that out. My presentation today, what I wanted to do is I just wanted to kind of share our experience. You're going to see a lot of graphs, a lot of plots. I'm not trying to make it any kind of word heavy. We didn't do any modeling. This is where we're at today. This is what's going on the daily. So let's get going. Not to belittle my Hawaii neighbors here, but this is over the past year. For the average user, residential user, we use about 500 kilowatt hours of energy per month. Kauai, where I'm from, here in Black, over the past year, the fruits of our labor have resulted in less increase as a result of higher oil prices that were going on last year. We've stabilized our rates for our members. We're a member-owned co-op. We're 135 strong, about a dozen engineers. Our drive for renewable energy was to stabilize our rates, hedge against the future price of oil, and not be coupled to residential rates based on the volatility of oil prices. So we, as a member, as a ratepayer, myself, when I started in 2009, our bills were $300, and I'm using 500 kilowatt hours a month. That's crazy. hard to see on here, but this is $40 million right here. If we generated all the power on Kauai in 2022 from oil based on last year's oil prices and compare that to what we did actually with what we did generate, we saved our members over $40 million just last year. So here's Kauai. Anyone been to Kauai? Oh, well, why are we having this conversation? So, so we've been busy. If you guys know to Kauai, you guys probably flew into the airport right around here. If you guys are looking over there, we're right around there. If you went to the Poipu, the Hyatt that's down here, you went to Honolulu, you're up here. Just kind of put things in perspective. Wettest spot on earth is right here in the center, Mount Waialeale. The windward side's primarily our wetter side. Over here on the drier side, on the west side, the leeward side, doesn't get a lot of rain, just to kind of put things in perspective. We've been going gangbusters from 2009, we were 9% renewable, till today we're about 69.5% renewable. A lot of it's been as a result of PV plus battery storage, and it's all been KIUC driven as kind of like the developer. We've been going out, we're making land agreements with large landowners. That's our strength, what we can bring to the table when we go and we do a project. Because we have like this aggressive drive to wean ourselves off the cost of oil. We've been going out and approaching these landowners. Hey, can we strike a deal with you folks? Oh, we can, great. If we make these terms and conditions and we make it for 50 years, can we pass it on to a third party? Well, you guys honor that because we're here for the long run. So that's what we bring to the table. We'll go out, we'll RFP, developers will come in. They'll then say, okay, like this will be the PPA rate. You guys accept that and we'll negotiate from there. But the land negotiations, all that leasing, the terms and conditions of all that, that's already been set up. Just to kind of say here, it's hard to read. I didn't realize it was going to be really hard to read, and this is really small font. But these two sites are basically running in grid forming mode right now. We have over 40 megawatts of behind the meter residential solar because people are continuing to put their own solar on their roof because prices are so expensive. Right now, rates are probably 37 cents a kilowatt hour still. Our single largest combustion turbine is over here in Kauai, and it's actually adjacent to the Tesla. They connect basically at the same transmission bus. So we got a Tesla virtual synchronous machine mode that we've had running there since 2018. And we dispatch that every 1 to 2 seconds. And it does offer the fleet of GFM services with its inertial response. Kauai, when we are running 100%, we do run that in synchronous condensed mode. We have had issues with it. I mean, it's been a learning curve for all of us. But when we're running 100%, that's running for short circuit stability, and we really don't know what inertia we need, but the more spin we got, we think the better. This is a typical day when we're running 100% here. This is in yellow is this is a good solar day. So this is a direct to grid solar here. In blue is hydro. In this orange color here, this is PV plus battery storage. So this is shifted solar energy to the off sun hours for dispatch. Green is biomass. And this gray color is diesel. But this is showing us running 100% renewable between these hours. I think this might have been 4 or 5 hours. The longest we've gone is over 10 hours in the daytime. We ran over probably 2,100 hours so far at 100% renewable. Our peak load here fluctuates. It's between 70 and 80 megawatts. 80 megawatts is our all-time peak. And here you'll see a little bit of gray right there. That's not a typo. When we run in synchronous condensed mode, we're spinning our generator, but there is windage losses because of the LM2500 and it's still spinning the turbine. So we still incur about a megawatt and a half of losses there. This is a good graph. So just to kind of throw it out there, and here in blue, this is our 24-hour load profile in blue. So you got midnight to midnight. In yellow is system frequency. In blue and red is direct to grid solar. Our direct to grid solar are our biggest pains right now. They're the ones that are moving our frequency around. And it gets really bad when you've got two of them moving at the same time. And this shows it. You can see frequency moving as we're getting the fluctuation in red and blue over here. You might start out sunny, things are good. We actually kind of be conservative. We actually will set point our frequency higher than 60 hertz because we know a frequency is going to go down when the sun starts going up and down with the solar. These don't look good. So anyway, my big thing at work, every morning I get in, I'm looking at DFRs. How did we do? Anything go wrong on the system? Look at our historian data, compare that to the high-speed DFR data. How did we do? Did we see anything that didn't go right? What do we got to do to fix it? Do we do some kind of adjustments? Do we got to forward it on to a PPA developer, and talk with them? Hey, what's going on here? We did things pretty simple. We operate our PV battery systems mostly in just a fast frequency droop response, volt var frequency watt. And then that's basically at the inverter terminals. Above that, we still will send dispatch signals. Here on top, we've got frequency. It's kind of hard to see here. This is a GPS time-stamped frequency plot. And in green and blue, we're actually showing two different frequencies. And it got me scratching my head. Why are we seeing two different frequencies on our system on the same grid and they're connected? This is our KPS unit. On this specific event, it tripped. And it was only pushing out 9 megawatts here, but it was enough to cause our DFDT up to about 7 hertz a second on our grid. Based on the green, not the blue one. On the bottom, you've got basically we've got our one grid following inverter. We've got our virtual synchronous machine mode inverter, and we've got another grid forming inverter on the grid. These are the 3-phase watt comparisons. As you can see, they're vastly different. So saying something is GFM versus GFL, like the other presenters were saying, I think Deepak was saying that. What does that mean? The devil's in the details. We were lucky enough to do a project with AES, Kelsey's group. That was last year, I think, out there on the base. The base had really stringent requirements. They wanted everything in the world, including Blackstart, unplanned seamless outage, unplanned seamless disconnection. They wanted seamless, planned seamless, everything. We proved it out. This system can do that. So if you guys are planning and trying to figure out how are we going to navigate, is this even possible? This project proves it's possible. The only thing that we weren't able to test is actually faulting our transmission line and seeing the response and seeing the thing disconnect and then self-island itself, the load. We were not able to do that, obviously, I'm not going to throw a chain on the transmission line. But it can do everything else. So this is showing planned grid tied to islanded. Look how smooth the microgrid frequency is compared to our system frequency in green. Even the microgrid voltage is pretty steady. This is 3-phase 12 kV voltage. That's the point of interconnection voltage there. This is planned islanded to grid tied, so reconnecting, resyncing back to the grid. You got your microgrid frequency here in blue, nice and steady. Sync occurs, breaker closes, boom, right back in action. Microgrid voltage. I think they issued the synchronization right about here. And you can start seeing it's synchronizing to the grid. Finally, when it gets in sync, boom, breaker closes. Now we're back in sync. Unplanned seamless islanding. This was the hard one. So this is basically saying we're not going to plan an outage, but we want you to be able to recognize that you need to disconnect from the grid and still power the load at the substation. This is showing breaker status. We just take the A contact status, bring that in the DFR, everything's timestamped. So this is showing here, this is the transmission breaker opening. This is saying as if there was a fault external of the substation. Below that in green, we've got the breaker status of the islanding breaker. You can see how quickly we basically send a transfer trip from our transmission breaker to the distribution breaker. Takes about 3 cycles. In here we have a megawatt and megavar of the grid forming inverter while it was grid connected. We're dispatching, we're supporting grid. We island the system and then automatically it knows where to go. So what we're doing is we take the CTs from the load and we feed that back into the control system. So the control system always knows what that load is, that if it does happen and it needs to island, it knows exactly where it needs to go to for watt and var. And then here's 12 kV voltage down below. You can see it doesn't change. This is looking at the microgrid voltage right here. This is it proving it can Blackstart. You can see the system shutting down in blue. And then it reconnects and Blackstarts the grid and island in this microgrid mode right here. You got microgrid frequency, microgrid voltage. And we even made sure that they could actually pick up the feeder loads in Blackstart. This is showing inrush on the distribution transformer on the feeder breaker. These 2 spikes here. This got me pondering. This is like fresh off the press. So it got me wondering, going back to that, the one plot that I had 2 different frequencies, I've been kind of pondering that, what's going on. So we were able to actually trigger a high-speed DFR data that samples at 7,680 samples a second, GPS time-stamped, and I was able to get all 3 major PV battery storage systems, high-speed records for all of them. And I was like, oh man, this is the honeypot. I'm going to see what's going on. But unfortunately, the DFRs they won't plot frequency at high speed. So I had to try to program something after talking with NRO. They kind of told me what they've been doing in Excel. So I went back to the drawing board and I programmed an Excel worksheet. And it froze my laptop after about 20 minutes of trying to calculate system frequency. But I was looking at the changes in angular velocity of the phase angle every 4 milliseconds. And I was doing that for like 18 seconds. So you can see why it took so long. So what I did is I called up our friends at Schweitzer and they said, oh, we think we can do what you're doing in Excel and just give us your algorithm. We'll program something in the the synchro software here. And they did. We filtered out frequencies outside of 30 hertz and outside 90 hertz to help smooth out our frequency. But now we're able to actually see what frequency is doing. Up here is A phase from 3 different sites. B phase from 3 different sites, and C phase from the same 3 different sites. We're seeing different frequencies per phase from 3 different sites in a short time frame. We don't know what's causing this, to be honest, but it's just something that is getting picked up. We don't know if it's an error in the CCVTs during the transient time interval. We don't know if it's a PT issue. We don't know what we don't know right now, but it's just something that's got us thinking of, is this something that we need to kind of, get on the radar of something that could possibly potentially cause some issues for us. So if anyone knows what's going on here, let me know. I think it has something to do with the phase jump. I do have phasor data for this as well. So happy to hear anyone out. Lessons learned so far. I'm a little bit late, but we've been learning a lot. I'm not going to read off everything here. You guys can read it for yourselves. We've been doing a lot of changes. We're small, we're nimble, we can pivot at our utility. If we see something that's wrong, we make a change. We've got 3 or 4 of us. If you guys ever talk to KIUC, you know the 3 or 4 of us you guys are talking to. You guys have been to Kauai, you guys have come to KIUC, you've met us. If we see something that's wrong, we fix it and then we move along. That's it. Thanks for having me here.
Thank you, Cameron.